Legion week. I want to spend more time today talking about the physical analysis. In particular, I want to do a deep dive on one particular part of the physical analysis, which is the part that we started looking at the last time, which was the update set physical analysis, which effectively is what is used, for every one of the region requirements that might be mapped by a task or a logical or a copy or anything that tries to map a logical region. The update set physical analysis is what is used to actually go talk to all the equivalent sets that represent the metadata for that logical region, figure out what instances need to be or what copies need to be issued to bring the instances up to date that we're trying to map for that logical region, and then issue all those copies and stuff like that, right? And just to refresh everyone's memory to make sure we're all on the same page, right? Like, effectively, we have a physical analysis for every region requirement that we need to analyze, right? So, like, if you're mapping a logical region for a task, we create in the physical analysis, we create, one of those update analyses to actually go perform that analysis. And it's going to go, to do some work on every one of the equivalent sets that are associated with that particular logical region. Right, and it's going to figure out what copies and fills and other stuff it needs to perform. And those will actually get stored in one of these copy fill aggregators, right? And then eventually, once we've analyzed all of the equivalent sets for the logical region, then we tell these copy fill aggregators to go issue their own copies and then update, the instance views with, the names of the copies and stuff that have been, or with the events that represent the completion events for those copies and fills and things like that. In general, there'll mostly only be one copy fill aggregator, but there can be cases where you get two, and maybe we'll get to that today. But if not, like, it's useful just to think that there might be just one copy fill aggregator that's going to be storing all of the update copies and fills that need to be issued from any of these equivalent sets that need to be performed, right? And to remind you why we do that, right? Effectively, the reason that we do that is because we might want to fuse together copies and fills from different equivalent sets, right? Different equivalent sets represent different sets of points, but we might want to fuse some of those copies and fills together because, Realm wants to see the biggest possible copies and fills for as many points as possible. So, effectively by aggregating, all those copies and fills that need to be performed in one of these copy fill aggregators, we can effectively accumulate all of them and then try and fuse them together before we actually kick them off to Realm, right? And so effectively, what we're mostly going to be looking at today is these EQ sets, but we'll also see where, the copies and fills get stored in the copy fill aggregator. And if we have time, we'll actually start to look at, the algorithm in the copy fill aggregator that actually starts, pushing those copies or fusing those copies and fills together where possible to actually issue them to Realm in as big a possible update as possible as we can. Okay, so this is the picture you should have in your head, and what we're going to do today is actually look at, for one of these analyses, looking at one of these equivalent sets, we're going to do the deep dive into, what the functions are that actually do this update, and then we'll see stuff get recorded here. Okay. All right. So if you remember, effectively every analysis has, a method that you perform the traversal on. So actually, let me jump up a level here. Right, and in particular, like for the update analysis, which is the physical analysis that goes and traverses all of the equivalent sets, associated with a particular logical region, right, that'll get invoked with this perform analysis call, right? It gets passed in, the equivalent set that's supposed to go talk to, an index-based expression that's supposed to traverse on that equivalent set. It might not be all of the points in the equivalent set, it might only be some of them, right? And if it is all of the points in the equivalent set, this expert covers will get set to true, otherwise it'll get set to false. You've got a field mask for the fields that you're supposed to be traversing over, and then you've got some, data structures for storing the events that, need to be, if we need to defer this operation till later, we can put an event in here and say, run this analysis again later once this event is triggered. And then you've also got, events recording when you've actually finished your traversal, like if you had any effects, for updating references or sending out messages or stuff, right? You can store events in there. So these are both output parameter arguments here. Right, and so effectively, this update analysis turns around and calls, on the equivalent set, it says, perform this update set analysis, right? And by the way, here's the name of my analysis and all the other arguments that I get passed in here, right? And so if we go look at update set, right, you remember we started looking at this method the last time, and we did the first pass here, which was the reduction pass. And on retrospect, I probably should have started with the simpler read-write case because it's actually much more canonical, right? So I'll just refresh everyone's memory. right? You might take an analysis or lock on your physical analysis here, right? And again, coming back to this picture, this analysis might be traversing multiple equivalent sets at the same time. So if you're going to make updates, like say to this physical analysis to store things, right, you need to have locked this analysis because you might be having multiple traversals of different equivalent sets happen at the same time. So that's the reason for that. We're actually already holding the lock on the equivalent set from the caller, so we don't have to worry about taking the lock on the equivalent set, and so that part is already safe. Right, and we talked about this part previously, but just to refresh everyone's memory, the first thing you do in this method is check to see if the equivalent set has been initialized. Right, like if you're accessing data that hasn't been initialized, we want to report that back as either a warning or an error if that's the case, because ideally you should only be accessing things that are initialized, right? And of course, if you're not reading, if you're just doing like a write only, this check initialized will be false, and so you don't have to worry about that. But this is where the check happens for the initialized data that occurs. So today, the last time we looked at the reduced case where your analysis was actually performing a reduction, but I think we actually want to skip down here to the last case, which is actually probably the most common one, which is the read-write case or read-only case where you're the first read-only if there are no guards. We'll talk about when you can have guards and stuff, but let's just assume we're doing a read-write case. That's a very common case. Effectively, imagine your task is mapping logical region with read-write privileges, so you need to bring your instances up to date and then record those instances as the new valid instances, because effectively if you're going to be writing to those instances, then you're going to be producing the most recent copy of the data for this particular equivalent set, right? So you need to invalidate all the other ones and so forth. And so the first thing that we do before we actually start doing any analysis, right, is effectively we check to see if we already have a copy fill aggregator, that's already been made. And if that's the case, we'll get a reference to it and keep it around, and we'll talk a little bit later about these clear update fields. But effectively it's saying, if we've already got a copy fill aggregator that we started making for this physical analysis, then we can reuse that here. But if not, it's okay for it to be null. We'll make it on demand, if we need to issue any copies or fills as we go down into this update set method. So effectively, you can have an input aggregator, but it's okay if you don't. It's just a matter of if you do already have one, you probably want to reuse it. And so that's what this little bit of code here is doing. So the next thing that you're going to do is you're actually going to perform this update set internal method. And this is actually what's going to issue all of your copies and then record, any of the instances that we've brought up to date as being the new valid instances, right? And we're going to go dive into this method because it's actually, we're going to recurse down through the call stack here for this method because that's actually most of what we want to do today. Before I go do that, though, there is some extra code here for handling things like restricted coherence. So if you're writing, you can mark that you've actually update the initialized data, and then there's some stuff for restricted coherence, which we'll probably not get into today. And at the end here, we can record some stuff about your aggregator. If we actually did have an aggregator and we actually issued some copies, we'll actually record some information about those here. And we'll talk about that part a little later. But the main thing that we're going to look at here is this update set method, because this is what's actually going to copy or bring all of our instances up to date if they are not already valid instances. So let's actually go take a look at that update set internal method. Okay, so this update set internal method, again, we're going to have to dive into some more functions in here, but let's do the high level version of this method because it actually, is pretty straightforward at a conceptual level. Right, so the first thing you're going to do is, for all of your instances that your analysis wants to bring up to date, they're going to be these target instances and these target views. And actually, I should have showed you, if I jump back to the previous method, one of the things that we did when we called this method down here, where was it? Here it is. One of the things we did when we called this method, we actually are pulling out a lot of things off that are stored in the actual analysis itself, right? So for example, like the target instances and the target views. So these target instances are the names of the instances that we're trying to bring up to date or check that they're already up to date, or if not, issue copies to bring them up to date. These are the equivalent view objects which store all of the users of those instances, like any previous tasks or copies that are reading or writing to those instances. Those views are the data structures that track those things. So we've got reference to all of those. Right, these source views are effectively a way for the mapper to say, if we do have to issue copies, I want you to issue copies from these things first. So that's sort of a performance optimization for the mappers. We'll see where that comes in. And we also grab some stuff like, the tracing info and whether to record things as valid and stuff in this update set internal method, right? And so if we go look at update set internal, right, you see it has a couple of additional parameters here, and these are the things that I just point out to you, right? Like we've got a list of our target views, our target instances. These are the instances that we want to bring up to date. And then we've also got, a list of the target views for each of those instances. And by the way, these two vectors zip with each other, right? So you might have you might have one manager, but you might have multiple views for that manager, right? So you have to be a little wary of that, but that's effectively what's going on there. So those are the extra arguments here. I guess the other things that are important, right? We also have this region usage method argument, which says like how are we using this logical region? Is it read write or read only, right? And so in the case that we're thinking about today, right now, we're doing read write. So this region usage will be read write most likely exclusive, saying we need to bring this thing up to date, and then we're going to be writing it, so we're going to be producing a new valid instance, right? And here's our pointer to our analysis and stuff. And we've also still got arguments about, the points that we're analyzing and whether those cover the whole equivalent set. And we've also got our field mask saying, what fields we're bringing up to date across all of these target instances and so forth. Right, okay. So what does this method do? Let me do it at a high level, and then we'll dive into all of the sub methods and so forth. So the first thing it's going to do, right, is we're going to have to bring we're going to check to see whether these instances are currently valid or not. And if so, and if not, we're going to issue copies to bring them up to date. So this make instances valid, right, effectively is going to do any copies or fills needed to bring the instances up to date with the previous, previous writes. And then on top of that, effectively, we need to check to see whether there were any outstanding reductions that were being performed. Right, and if there are any reductions that are outstanding on this equivalent set, well then we need to apply them. Right, and so this apply reductions method is going to go and then apply those reductions on top of the instances to bring them up to date as well. Like you have to apply all those reductions to bring them up to date. This is just like handling cases where we need to invalidate reductions and so forth. So we'll come back to that part. And then down here at the bottom, right, effectively if we're writing, right, then one of the things that we need to do is we need to filter all the previous valid instances, right? Because effectively we're going to be producing a new valid copy with our task or our operation that we're producing here, right? We'll skip this restricted case, that's restricted coherence, so that'll be a discussion for another day. But this is the common case here where, effectively, if you're writing, you need to invalidate all the prior instances because they're no longer going to contain valid data after that, right? And so you need to filter those valid instances. And then, record ourselves as having new valid copies of data, right? And this can happen in either the read-only or the read-write case, right? Like effectively, if it's a read-write case, then, it's obvious you produced a new valid copy, and you're just going to go through, again, let's skip the restricted coherence, we'll be in this branch down here. Effectively, you're going to record all your valid instances, but also if you were doing like read-only, right? You've now maybe potentially produced a new set of valid instances that are now up to date. And they're a new copy that you also want to record for other future users that might want to do them, right? And there are some cases where the mapper may have said like even though I've asked that this task be brought up to date, or these instances be brought up to date, I don't actually want you to record that they're valid, right? And this can most commonly happen in the read-only cases where mappers are allowed to say like, I want to make a read-only copy of my data, but I don't want it to be considered valid after the end of the task, right? Because maybe I want it to be eligible for garbage collection and so forth, right? And so you might not actually end up, recording that you've brought these instances up to date in this equivalent set and say that they're not actually valid. Well, they will be valid for the purposes of this one task or other operation that's mapping them. They're not going to be valid, after that point, right? And so we won't record those in that particular case. Right, so this is pretty standard stuff, right? Like, if you're writing, you invalidate, prior things, and then you record, that these are new valid instances in this equivalent set, that they contain the most recent data for this particular thing, or this particular equivalent set, right? So effectively, that's the high-level structure of this update set. It should make conceptual sense. The next thing to do is to actually start diving into some of these methods, like make instances valid and apply reductions, so we can actually see how they actually work. But at a high level, at least you have a picture of what's going on, right? So let's go look at this make instances valid method next. And what we're going to see is it's going to do two things. It's going to first check to see whether those instances are already valid, like they've already got the most recent data. And if not, it's going to go ahead and issue those copies to bring them up to date. but ignoring the reductions, right? The reductions will be handled separately by this apply reductions method, which we'll hopefully also get to today. Okay, let's go look at make instances valid. Okay, so here's the make instances valid method. Again, lots of arguments to this method. Trying to be very explicit about what we're trying to do here. Most of these arguments we've already talked about. There's one new one here, which is the skip valid check. There's some cases where make instances valid is called, like for example, in like a copy across case where you don't actually need to do the valid check to see if the data is already valid because the instances are potentially coming from like another region tree or something like that, and so you can actually skip some of those checks. But for the common case, for the case we're caring about here with update analysis method, this skip valid check will be false, and so we'll definitely need to do this analysis. Okay, so what we're going to do here is we're going to iterate over all of our target views. So for every one of the target views that we're trying to bring up to date in this data structure here, right? Effectively, for every one of these instances that we're trying to bring up to date, we're going to iterate over these target views. The first thing we're going to do is check to see, if the valid mask for those target views is disjoint from the update mask that we're trying to perform here, right? It might be the case that, we're traversing. Let me come back to my picture here. When your physical analysis is actually doing its traversal, there might be some equivalent sets that only need to be traversed for a subset of the fields in certain targets, right? So like, this physical analysis might be bringing, say, 2 instances up to date for different fields, like field A and field B, right? And so we might need to traverse like these 3 equivalent sets for instance A and maybe these 3 equivalent sets for instance B. Right, and so in some cases, you might only be traversing an equivalent set for one of the target instances, right? And that will be reflected in the fact that that field mask will only be set, for field A, right? And so you will only need to analyze the targets for field A and not the targets for field B on this particular equivalent set, right? And so this check here is effectively just filtering out any targets that don't have any valid or any fields that we're not trying to analyze on this equivalent set, right? We can kind of skip them. Right, and so by testing for disjointness on the field masks, right, this little star here, we've overloaded the star operator just to remind everyone, right, like that's just testing for disjointness on these 2 field masks. So if these 2 bit masks have non-overlapping sets of fields, right, then we can, that this will evaluate to true, and we can skip this part of the check right here. Okay, but assuming that's not the case, assuming we actually have fields to traverse on this target views, right, well then we're actually going to go iterate over them and find them, right, and so we can get the view for this first instance, right? And we can get, the mask associated that we need to do the traversal for, right? So we're effectively saying, for this target view, intersect the bit masks with our update mask, and that gives us a new mask, right? And if that is not empty, right, then we can actually, if it's empty, then we can skip it, right? But if not, we're going to come down here and actually do the analysis. Okay. Here's the skip valid check, which effectively is saying, if we're allowed to skip this check, we can just go do it, and we're going to just start issuing copies because that's what we actually need to do. But in the case where we're actually mapping like a new logical region with read-write privileges, we actually do want to do this check because we don't want to issue copies necessarily, right? If the data is already valid for some or even all of this physical instance that we're trying to bring up to date, well then we can actually then we don't actually have to issue any copies, right? And so we can keep going without needing to do anything, right? And so the first thing that we'll do is we actually do this find fully valid fields check, right? And what this is going to do is check to see, like, for this particular target, for these fields, for this expression, and this, whether this expression covers all the points in this equivalent set, check to see if, this instance is already considered completely valid for all of those points, right? And so let's actually take a look at that find fully valid method. Okay. So here's the find fully valid method. You can see it's actually fairly simple, right? And effectively it says, first things first, check to see if we can find the name of this target in the set of total valid instances for this equivalent set. If it's already in the set of totally valid instances for this equivalent set, well then perfect. That's, that means that we know that it's already completely valid for all of those things. You're not quite off the hook yet, right? You do need to check to see if that's true for all of the fields for that instance, right? And so effectively you look at the instance mask that got passed in, right? And you can subtract off, all of the fields that were already in this total valid instances set. Effectively, all of those fields are now considered valid. We can remove them from the mask that we need to, of fields that we need to bring up to date. If that mask is empty, that's great. Then we're done, right? Effectively, we can return true saying, all the fields on that instance were already done. are already up to date. They were already in the total valid instances set, and so therefore, this target is already up to date for all of those fields, and we're completely done, right? But if not, if that's not the case, right, well then maybe let's see if we can check to see if it's valid for the points that we actually care about in this index-based expression, right? Now, in the case where this index-based expression doesn't, we only want to do this in the case where it doesn't cover the entire set. Like if this expression doesn't cover all of the points in the equivalent set, right? Because if it did cover all of the points in the equivalent set, then the only way that this instance could have been completely valid would be for it to be in this total valid instances set, right? So like there's no point in doing this partial valid check, right? If our expression of points that we're trying to check for are not, do not cover the entire equivalent set, right? So effectively, only in the case where we're checking for a subset of the points will we go look in the partial valid instances and check to see if it's up to date, right? And so in that case, if it is the case that we're only checking for a subset of the points to be valid, right, then we can actually do this partial check, right? We check to see if we overlap with any of the fields in the partial valid set. If we do have overlapping fields, then we'll go dig through, all of the different expressions and check to see if they actually do dominate effectively the expression that we're actually trying to analyze here, right? And so this find fully valid is effectively doing a check to see are all of the fields for this instance for this expression completely up to date, right? And it will return true if it does and false if it's not. And you'll notice that this check is actually not completely precise, and that's okay because effectively we're going to do the more precise check where we actually union together index-based expressions to see if they actually accumulate to all of the valid fields a little bit later. And so we'll handle that part a little bit later. This is sort of like a common case, but imprecise check to see if it's valid for all of those fields. Okay, so let's go back to make instances valid. I can type here. Okay, so effectively, if the instance was already valid for all of its fields, for all the points that we cared about, well then great, we're done. We can go right back around this loop and start doing the next one, right? And we don't have to do anything, right? But if it's not the case that it's fully valid, right? Well, now we need to actually find any expressions for points and fields for which this target instance is partially valid. Right, like if there's already some valid data in this instance, but maybe it's not completely valid for all of the points and fields that we care about, we actually need to do that. We need to find the names of the stuff that it is valid for, so that then we can go and issue copies for the stuff that it's not valid for, right? So let's see. I'm actually going to skip this branch here about collective instances, this little blob of code here, because the collective instances and view stuff is a little tricky, and for our purposes today, it's probably not particularly relevant. We can think about things just in terms of normal instances and stuff like that. So anytime that you see this check for collective instances and stuff, you can probably for purposes of initial understanding, you can actually skip some of that. So let's skip that part here. Our goal is still to fill in this partial valid expressions, right? So this is one of these field mass set of index-based expressions. So think of, for every one of these index-based expressions, there's a set of fields that it applies to, right? And this is going to define the sets of points and fields for which we have, valid data on this particular instance. We're trying to fill this in, right? So effectively, the next bit of code that we're going to do is we're going to go and find all of the names of expressions and fields that represent valid data for this particular target instance. We're going to populate this partial valid expressions to say this instance is valid for these fields and on these expressions. And from that, we'll then figure out what copies we actually need to bring up to date. So let's actually take a brief look at find partial valid fields here. Okay. So here is find partial valid fields. Again, we've got our target instance that we're trying to bring up to date. We've got our mask of fields that we're still trying to check for. These are the sets of points that we're trying to check for on this field, and we're going to try and populate this partial valid expressions, right? Okay, so the first thing we're going to do is check to see, is it the case that we can find this target instance in the set of partial valid instances, right? And hopefully we do, because if we don't, there's not really much we can do, right? So this if branch, right, effectively, if the target doesn't even appear at all in the partial valid instances, well then, you're done, right? Effectively, you're not going to find any valid data, so you can skip all the rest of this, right? And so this if branch reflects that, right? Okay, but let's say we do find it. Next thing we do is we do a little a quick test to see, are there any overlapping fields in all of the partial expressions? If not, we can skip that again because like then there's no point in traversing over anything because we know there's no overlapping fields for us to care about, right? So there's nothing for us to do there. But let's say, the common case is that there probably are some partial overlapping fields, right? So now what we're going to do is we're going to iterate over the existing field mask index space expressions for all the fields, right? And see which of those apply to this, we're already for this target instance, so see which ones overlap with the things that we actually are checking for to see if they're up to date. So the first thing we do is we do a field mask test, right, to see if there are any overlapping fields, right? We bitwise intersect our two field masks, the ones that we're testing for, as well as the one for, for this index space expression that we're analyzing. If they're not overlapping, then we can skip them and go on to the next one. The next thing we're doing is test for overlapping points, right? So this expression overlap, test is effectively going to be the set of overlapping points for this expression with the points that we're testing for versus the ones that are already valid, right? There's a fast test and a slow test, right? Effectively, if we know that the expression covers, right, the expression that we're covering for, the expression that we're testing for covers the entire equivalent set, well, then we don't even need to do any index-based math. We can do this fast path and just say the expr overlap is the same as, the expression that was stored in this this partial valid set of instances, right? And so we can just store that. But if it doesn't cover it, well, then we need to do an intersection, right? So we actually intersect, these two expressions and get them back. And we've got a little test here for empty for handling that case, right? If it's empty, then there's nothing for us to do. We can continue. If it's the same, as the original expression volume that we cared about, right, then we can, that's going to dominate, right, our existing expression, right? So effectively, like if the intersection dominates the expression that we're testing for, that means that we've covered all of those points, and then we can remove those fields safely from and say that they're already valid. And if the the instance mask has gone to 0, saying we've tested all of our fields, well then we're immediately done, right? So that's a fast path out. But in the worst case, right, we actually say that like they're not the same, and we actually gotta, or actually I should say that the worst case is like this expression overlap doesn't change. There's a special case here to help with some name aliasing and stuff, but this is a performance optimization where you can say if the intersection volume is the same as the expression that we that's already valid for this instance, then we can just reuse that expression and not need to make a new name for this expression with this intersection. That's kind of a performance optimization. Okay, so if you make it down here, what that means is that you've effectively found an expression that is partially valid for this target instance, which means that only some of the points are valid for these fields, but not all of them, right? And if that's the case, then you actually do need to effectively store it in the set of in the set of partial valid expressions, right? So we want to add it into the set of partial valid expressions, and we do something here to actually maintain an important invariant, and that is that we actually try to maintain that for every field there's exactly one expression in this field mask set that represents the valid fields. Or the valid points for that particular field, right? And so we only want to have one index-based expression for each field in this partial valid expressions. So you can't just go and insert this, directly, right? I guess you can't. You can in one case, which is that if you detect that this partial valid expressions data structure that we're trying to populate here doesn't have any entries for these fields, like the set of overlap fields that we tested before, if there aren't any fields in there, then you can just jump right to this statement here and insert the expression right away, right? But if there are overlapping fields, well then you've got to go through and add them in a way that deduplicates expressions that share the same field. And if you detect that you have fields that are shared, right, then you union those two index spaces together, and then you can insert the new unioned index space into the data structure, right? And so this code here is doing that deduplication to make sure there's exactly one expression for every field stored in that partial valid expressions. Okay, and by the time you finished all this loop, what you've got is you've populated this partial valid expressions data structure so that you know the names of all of the valid expressions for every field for this particular target instance, right? And so we've got the set of all the fields and points that are currently valid for this target, right? And this may be empty, right? It's entirely possible that this is empty. And in fact, like in the common cases, I would say it actually probably is empty, but there are uncommon cases where you have partial overlaps and you've got, effectively some of the data is valid for the instance, but not all of it. Okay, so let's jump back to make instances valid so we can actually like see what we do with this data structure now that we've populated it, right? So just to remind you, we've called this find partial valid fields, and it's populated this partial valid expressions. And by the way, if we determined that all of the points and fields were already valid from these partial valid expressions, then this method would have returned true, and we could have skipped past this onto the next target, right? But if we get here, right, what this means is that our instance is not completely valid. It might be partially valid. It might have some fields and some points that are already up to date, but not all of them are. And so we need to actually start, going through and doing the analysis to actually issue any update copies to bring, those remaining points and fields up to date, so we have valid data in all of them. Okay, so let's see. So what we're going to do now is we're actually going to compute this needed expressions data structure, which is going to be the complement, effectively, of this partial valid expressions, right? Effectively, it's going to be the sets of points and fields which need to be issued copies to bring them up to date, right? And so how do we actually go and do this? Okay, well, what we do is we first break all of these expressions into what are called field groups. And actually, this is pointing out to me that I actually think we could probably do an optimization with this find partial valid fields that I was pointing out before. But I'll come back to that another time. But effectively, what this is going to do is going to sort, for every one of the expressions in this partial valid group, what it's going to do is going to compute, a set of expressions that all share the same fields. So that point where I guess the optimization I'm thinking of here that I'm noticing that we might need to be able to skip is, before I told you this partial valid expressions had exactly one expression for every field. And this code here is actually designed to handle a case where that's not actually true. So I might actually be able to remove that restriction inside of partial valid fields. This code will actually try to sort, it'll create one of these Legion list of field sets. And what this is doing is it's saying, for everything in this partial valid expressions, let's say we had multiple expressions for every field, saying like this field was valid for some points, for points in set A and some points in set B, right? It's going to sort, those expressions into expressions that have the same fields, right? It's effectively like a group by operation is really what I should say. This compute by field sets is like a group by on the fields. And effectively it says, these are the expressions that all share the same fields, and it puts all the expressions that share the same fields in one of these field expression or field set things in this list, right? And so what you get is a list of these field sets, and each of these field sets has a set of fields that all have the same expressions, right? And that's what these expert groups are, right? And so effectively it does that group by operation for you on this universe of all potential fields. You can actually make the universe smaller if you wanted to, but most cases you don't. And so this group by does that, and then what you end up with are these effectively groups of expressions for common fields that all have the same sets of expressions, right? Okay, and so what's actually happening here? Once we've done that group by operation, we're getting a union expression of all of the elements, all of the expressions in this group, right? So these are all fields that all share the same expressions. We union all those expressions together to get all of the points, which they all share, right? And that gives us the valid expression, for this particular set of fields. And then we can subtract that from the expression that we're trying to bring up to date, right? And that needed expression tells you the remainder sets of points for these fields that have to be issued copies to bring them up to date, right? And if that's empty, we can skip it. We should actually probably put an assertion here that should never be true. We should never actually hit this code, right? And then that needed expressions can actually effectively then we store that needed expressions in this needed expers data structure. So this says for this set of fields in this group by, right, then this is the expression for the points that need to be brought up to date for those particular fields. Right, and at this point, we've got the set of needed expressions that actually need to be up to date in order to perform this copy, right? And again, this should probably not. We should never actually have a case where this is empty. I think we should always have found, whether if there's data here, then that means that we should always have expressions that need to be brought up to date. Now, a very common case in here is actually and this code, looks pretty complicated, but it actually will handle the path very quickly. The case where you actually have if you had no partial valid expressions, you actually would have skipped all this code, right? and we would just say we need to bring the whole thing up to date. So like, that's actually a pretty common case. But yeah. So we'll actually skip over like some of those cases. Or actually some of those cases will actually happen pretty fast in here. So this code looks complicated, but in the common case, you'd actually skip over lots of the logic in here. But in the cases where it will handle the cases correctly, where you have like lots of partially overlapping fields and instances and stuff like that. Okay, so we've got this needed expressions data structure. Now we need to start issuing copies to bring that up to date. Again, this is a blob of code here for collective views, and we're going to skip everything having to do with collective views here, right? So everything down to this this branch, or to this end of this scope right here, is all part of this collective view stuff. So we're just going to skip over that, but this is handling some stuff for collective views, for aliasing of names and stuff. But effectively, like if we get down here, right, then we need to actually issue the update copies and fills to bring those needed expressions up to date, right? And so you can see down here. Let's see. So if we still got remaining stuff here, right, then we're going to need to issue copies to bring these particular needed expressions up to date. Actually, did I do the right scope here? No, I didn't. Actually, sorry. I didn't show you the right closing scope for this if branch here, for this collective view thing. So here's the if branch, and this is the else branch, which I actually want to show you, right? So effectively, that will go through this needed expressions case here. We're going to actually issue updated copies for all these needed expressions. And actually, I should have pointed out here, we actually only populate this needed expressions data structure here in the case where these partial valid expressions are not empty. Right? In the case where they are empty, what that means is that like all of our instances, like all of our points for all of our fields still need to be brought up to date. And the way that gets handled is that this inst mask never gets filtered. Like effectively, this inst mask will continue to contain the fields, saying we need all of the points for those fields. And that actually gets handled as you exit the scope here, the skip valid check, right? And effectively, if you've still got valid fields here, then you end up calling issue update copies and fills here, saying, bring this up to date for all of the points for all of the things still in the inst mask. But, right, effectively, we're going to do the fast or the shorter path here where we actually had some partial valid things, in which case, if we have needed expressions, right, then we're going to call, issue update copies and fills with, our new expression and our set of fields for that expression that we need to bring them up to date. Right, so issue update copies and fills will actually go and issue the copies and fills for any of these, for a particular expression and a set of fields to actually bring this instance up to date. Right, and in the common case, I would actually say, like, if an instance is not valid at all, right, it will come down here and end up hitting this path, right? But in the case where it has partial valid stuff, it'll actually go through here, right? If you had some fields that were partially valid, you might do that for them here, and then if the remainder fields didn't have any valid points, right, then they would come down here into this path down here to issue update copies and fills down here. And that's reflected in the fact that, like, here we have the full expression that we're trying to bring up to date, and the inst mask of the remaining fields need to be brought up to date. Whereas here we have an expression coming from this needed expressions, and we have a set of fields for that particular expression that we need to bring up to date. Okay, so let's see. The next thing to do is actually go look at this issue update copies and fills to see how it actually starts to perform the copies, right? So let's actually go dive into that method. Okay, here's update copies and fills. Okay, so again, we've got our target view, our target manager, any source views the mapper asked us to pass in. We've got our aggregator, our analysis. I'm going to skip over this guard stuff. Again, that'll be a topic for later. We've got our expression that we're trying to issue any copies for. And note, this expression may not be the same as the original expression that we're doing the analysis for, right? This might be only a sub-expression saying we only need to update copies for a subset of the points that we were originally analyzing, right? Because some of them might already have been valid. And again, we get an update mask. And again, this might also be only a subset of the fields that we were originally analyzing. This update mask might say we're only bringing this particular expression up to date for a subset of those fields. Okay, so this is the part where we actually start trying to record copies in our copies and fills in our copy fill aggregator. So we're going to start doing that. There is a path here. So one thing that mappers can do, right, and this is where this source views argument here that has been passed down all the way from the analysis comes into play. So in some cases, mappers might say, I don't want to wait for the callback. Effectively what's going to happen here is we're going to find a bunch of valid instances, that we could potentially issue copies from to bring this particular target view up to date. And normally we would do a callback to the mapper to say, please tell us, the order in which you want us to try to issue copies from those things, because some of those source instances might be closer to our target and therefore better for getting performance. But the mapper might also pick a one that's farther away if it's going to have less contention or something like that. And so we ask the mapper to pick which source instance it wants to use. But some mappers don't want to wait for that callback. They might already know what their preference is, and so they're allowed to pass in their preference here with the source view, right? So effectively in your map task or map copy mapper call, there is a way to say, like, effectively, this is my preference set of source views for you to use when you actually need to issue copies from the current valid instances to bring a particular target instance up to date. So I would say, like, the common case is that this data structure is actually mostly empty most of the time, but there are mappers that do try to prefix and say, like, I'm giving you my preference ahead of time, so you don't need to even bother doing the callback. Just go ahead and analyze these views in this order first and see if you can issue copies from them first before you try to issue copies from anything else to bring it up to date. Right, so if the source views is empty, what we're going to do is we're actually going to check to see for each of those source views, are they already valid in this equivalent set? And if so, we'll record any copies to bring them up to date. So effectively, we iterate over these source views. We check to see, like, is the source view already in the set of total valid instances? And does it have any overlapping? So if it's already in the set of total valid instances, and it has some overlapping fields with the analysis that we're trying to do, like in this remainders data structure, right? This remainder stores the sets of expressions and fields that we still need to bring up to date. Right, so if we still got valid fields, then effectively, we can actually say, okay, great, we can issue the copy directly from this particular source instance because the mapper said we can do it in this order, right? And so we can iterate over the expressions. We can find their overlapping fields. If we don't already have a copy fill aggregator, we'll make one, and then we record an update. This record update method is actually what will store effectively store or record the fact that we need to do a copy from this particular source instance, to this target instance for these set of fields, for this particular expression, right? And record any reductions and any tracing stuff that we need to do, right? And so let me just actually do a brief digression and show you that over here in this copy fill aggregator class. Oh, here's copy fill aggregator. It's got a bunch of subtype or nested types in here, but effectively it has these record update methods. So record update effectively is a way of recording the fact that this copy fill aggregator will need to issue a copy from this source view to this destination view for this mask, or for this set of fields, for this expression, right? And if you're doing any tracing stuff for reductions and so forth, right? And then it has some helper methods down here that we'll actually encounter very shortly, but it has these first for effectively recording updates from a set of fields, from a set of source views, and then also recording partial updates from a set of source views, right? So we're going to encounter these two other methods here. But the one we see here is just like record that we need to issue a copy, right? Between those two instances, right? And we'll be able to, that doesn't actually go and issue yet. It's just going to store it in the data structure and then be able to fuse it later once we've actually finished all of our traversals. Okay, so effectively you do that. There's also a path down here to handle, partial valid instances for source views, right? So effectively, if you have if the source view is partially valid, right, then we'll still try to issue copies from it. And I'm going to skip over some of this logic because it's mostly variations on what some of the stuff I already showed you before for testing for whether expressions and fields are partially overlapping, and can you issue copies from all of them, right? You can only issue a copy from one of these source views if it actually is already valid. So you effectively have to do that test to see is it already valid and stuff like that. And so it does a bunch of that logic, but effectively if it gets to the point where, well, I should say, like, effectively it will actually record, if it can issue copies from that source view. Okay, so I'm going to skip down here and I'm going to leave, some of this for cases, or some of this for you guys to look at, on your own time. But effectively, that's what this if not source views as empty case is doing here. It's pre-issuing copies from those source views if needed. Okay, and where was the end of that else statement here? Here it is. Okay. So at this point, if we've gotten here and we still have some remainder or we still need to issue copies, right? Then like the first thing that we're going to do is check to see, what instances we actually want to issue copies from. And there's a little bit of a preference here in Legion, which, some mappers, nobody has complained about this yet, but Legion is maybe doing, depending on your interpretation, a slight violation of its mapping policies, right? So normally Legion would say, okay, you've got a bunch of instances that are currently valid, and there might be some that are totally valid and some that are partially valid, right? And if so, then we want to ask the mapper to pick which ones to try to issue from, so they can prefer maybe issuing copies from the closer ones before it actually issues copies from the farther away ones. And we actually do a little shortcut here. We actually make a slight variation on that. And what we do is we say, we'll give the mapper choices, but only if all the instances are either totally valid or all the instances are partially valid. So effectively, if we can find an instance that's totally valid, that for bringing this target instance up to date, right, then we'll only consider totally valid instances. If there are multiple totally valid instances that we could use as source instances to bring our target up to date, then we'll ask the mapper to choose between those. But if there's only one, we're just going to go ahead and use that, because we do kind of prefer bulk copies that move lots of data versus lots of little copies, right? So effectively, if you can find at least one totally valid instance to issue a copy from, we will not even go look at the partially valid instances, because it's much more expensive to go do that, right? And we would prefer to just issue a copy from one of the existing totally valid instances before having to go analyze all the little partially valid instances to see if to use them as sources to bring this thing up to date. Right, so effectively, the first thing we do is check to see, are there any fields for which this update mask overlaps with the total valid instances mask? And if there are, right, then we're going to make our copy full aggregator, because we know we're going to issue a copy, right? Then we'll go through and we'll find all of the totally valid instances that overlap with those fields, right? So we have this total instances, which are these are all of the instances that have at least a complete overlapping with the fields that we're trying to bring up to date. And once we've got that, then we can actually tell our aggregator, please record copies from these totally valid instances, right? And then we can actually go and filter those fields from the update mask, right? And if they're update mask, if we've actually recorded copies from all of the different fields, well then we're done, right? Like effectively we can actually return from this process without even looking at the partially valid instances, right? I'll actually I skipped a little else statement here, like effectively if they actually if our total field equals all the instances in the total valid instances field, we can actually just ask the aggregator to look at all of the total valid instances when recording its updates, right? So we can actually just pass in the whole data structure here. So that's like a little optimization there. And let's actually go look at this record updates method here. Now I'm running out of time, but let's actually take a quick look at it here, because this will actually show you where we actually do the callback to the mapper to actually have it sort through those instances and actually pick the right ordering for things. Well, so if there's only one view in that data structure, that's really easy, right? Like effectively we can just record a copy from that source view and we're done, right? But in the case where we actually have multiple different views, or multiple different source instances that we could pick from, right? We actually need to sort those, right? We again do this group by on fields, right? So this creates another one of these field set things. So effectively, again, it's doing a group by on fields, so you get the sets of views that are all sharing the same fields, right? And once you've done that group by, right, then you can effectively check to see if there's only one option for those fields. Again, really simple. You can record that update. But in the case where there's multiple views, well, then we need to sort them. I'm going to skip this deferred view stuff because that happens only in some rare cases, but might occur with like fills and stuff like that. But we'll skip the deferred viewed stuff, but let's look down here at the case where we actually have like just normal instances, right, as potential source instances. Again, if there's just one, then we can do the fast path. But in the case where we actually have multiple choices, like you could actually issue copies from multiple source instances here, right? Well, then we need to actually go ask the mapper which order it wants to consider those potential instances for actually performing the updates from, right? And this will actually call the select sources method, which is actually going to produce an ordering of of which order to try and issue those copies from, right? And in the case, and so if we actually go look at that, there's actually we're actually preparing lots of the arguments here to the mapper, but eventually you get this, effectively this callback to the mapper, this analysis arrow select sources. That's a callback that will actually go back to your mapper and ask it to pick the ordering of which those source instances will be considered for actually issuing the copy. And then we have some code down here to actually check to see like did the mapper give us reasonable output, and if not, ignore the stuff that didn't give us our reasonable output. But ultimately, it creates this select sources result, which is an ordering of those views, right, that effectively were produced from the mapper, and we will go and record the updates in that order that the mapper actually produced, saying what order to issue copies from those particular source instances. So anyway, that's just something to keep in mind. I'll actually point out one other thing here, which is there is a cache on this query, right? So effectively, if you have the same sets of instances that get queried multiple times, right, like we can actually, the copy fill aggregator will actually, deduplicate those callbacks to the mapper to actually help you realize that, like, effectively, we've already done this call and presume that the mapper is going to make the same decisions, with the same target instance and the same source instances over and over again. So just something to be aware of there. Okay, let's jump back to issue copies and fill, or issue update copies and fills, because we are running out of time here a little bit. Let's scroll down to where we were before. Where were we? Right. So we did the total. Effectively, if we've got if we've got total valid instances for some fields, then we'll just handle them, right, and issue copies for them. But if not, then we'll actually need to go do this for the partial valid instances as well. Okay. And so here, okay, so here's, this code gets really hairy. Hopefully most Legion codes don't actually run through this path, but there are some that do. In fact, we found bugs in here and stuff and have fixed them. So effectively, like the partial valid instances, right, we're gonna have to look through all the partial valid instances and find the ones that cover, sets that actually are, so effectively we're gonna break the partial valid instances into two sets. There'll be the ones that, there's some partial valid instances that might already cover, right, the expression of points for some fields that we actually want to bring up to date, in which case those are kind of like another kind of totally valid instances, except they're totally valid just for the set of points and fields that we care about, right? And so those will be the set of covering instances. And then in the really bad case, we might have some instances which, where the source view that's valid, is only valid for a subset of the expressions and a subset of the fields, right? And so we're going to effectively sort into these two different sets. Right, so we iterate over all of the partial valid instances, right? Check to see if they have any overlapping fields. If they don't, we can skip them, right? If they do have overlapping fields, then we're going to iterate over all the expressions that they're valid for. Again, for each of those expressions, check to see if the fields are overlapping. Do the test to see, if the expressions actually cover, right? And in the really nasty cases, you have to do an intersection to test to see, like, do those two expressions overlap with each other? If the overlap volume is non-zero, check to see if we are partially overlapping, in which case we have to record it in that set of partial instances. Otherwise, we can record it in the set of cover instances, right? Eventually, you get down here to these, cover and partial instances. If you've got cover instances, you can kind of treat those as the partially, or as the same as the totally valid instances, right? And you can just say to the aggregator, call record updates from the set of covering instances. And that'll work the same as it did up here with those total valid instances, right? So here was like the record updates from like the total valid instances, where you could say like, these instances handle all the points for all of those fields, and you can just go and handle those, right? And then this is the really terrible place to be, where like you're gonna have to issue a bunch of little partial updates, and you'll have to record, some copies from some fields, or some copy from some source instances and some copies from other source instances, even for the same field. Right, and that's a really, really nasty place to be, and that gets handled by this record partial updates method, right? So if I search for record partial updates, you'll see that this code actually does some. It's effectively trying to find groups of instances that effectively will do the right. Will issue updates for all the fields for all the points, but in some order that the mapper actually cares about. And so I think I'm actually running out of time here to go into this method, I think. Let's see. Yeah, so I think we might have to leave this one for a future date, or leave this as an exercise to the reader to handle the partial update case, which is kind of nasty, but is just a variation on what we've already looked at before. And we'll eventually, just to close the loop here, by the time you get down here to the bottom, you're just calling record instance update, kind of like you would be in a normal. This is again recording copies and stuff that you need to perform in this copy fill aggregator to bring the target instance up to date. Right, and so by the time, let's actually pop the stack here a bit, just to close to close the loop, right? So by the time you finish this update copies and fills method, right, this copy fill aggregator has recorded any copies that are needed to bring this target instance up to date. It hasn't actually issued them, but it's just stored them in this copy fill aggregator and made a copy fill aggregator, by the way, if necessary, to store all those things. Right, and so this issue update copies and fills has filled in, or has recorded with that copy fill aggregator all the copies needed to be performed, right? And if we're looking here at make instances valid, right, you can remember that the issue update copies and fills were all at the end of this this loop iteration here, right? And so it's brought this particular target instance up to date, right? Which we would then go around and do the next target and issue any copies to bring it up to date and do the same thing. Right, and by the time make instances valid is done being called, if we go back to update set internal, right, by the time this make instances valid up to date has been performed or it has returned, this copy fill aggregator here has been populated with all of the copies and fills that need to be performed to bring all the target instances up to date for its particular operation, right? And the next thing that we're going to do is we're actually going to do the same thing for reductions, and so we'll probably have to do that the next time. But effectively, we'll have recorded all of those copies and fills and brought them all up to date for all of the points and fields and stuff that needed to be updated for all of those target instances. Okay, so next time we'll do reductions and see how they get recorded, and then we'll go look at the copy fill aggregator to see how it actually does some of the fusion to group things together, and then it's going to have to issue these copies and fills in the right order. And just to mention, one interesting thing about this is you're going to have to make sure that these reduction copies are applied on top of any normal copies or fills performed by this make instances valid, and we'll actually see how the copy fill aggregator handles that. So it actually records copies and fills in the order that they need to be performed, and will actually fuse things in the right way. And so we'll go look at that the next time. So with that, I'm at time. So are there any questions before we wrap up for today?
Sort of not that crucial, but this expression covers thing. Can you remind me what that?
Yeah. So
why that's said and what.
That's giving us a special case, which is. The expression covers says whether this expression that we're doing the analysis for, right? So this expression is coming from we're analyzing for a particular logical region. It says whether this expression that we're doing the analysis for covers the entire equivalent set, right? So if I come back to the picture up here, right, we might be analyzing a particular logical region, right? And that logical region might, dominate, let's say, these two equivalent sets, but partially overlap with these two equivalent sets, right? And so in that case, when we analyze these two equivalent sets, expert covers will be true because the expression that we're analyzing for that particular logical region will cover the entire equivalent set. So this expression is effectively the same as the set expression for the equivalent set, right? But in maybe these cases, right, maybe the logical region only partially overlaps, right, with these two equivalent sets. So there, the expression will be a subset of the points for the entire equivalent set. Right, and so
and that allows you to shortcut some logic.
Exactly, you can
say if I have only a partial coverage, then I know there's something to do. Otherwise,
it's effectively a fast path for not needing to do intersections of points and stuff. If you're analyzing for all of the points in the equivalent set, then you can skip a lot of the intersection testing and subtractions and differences and unions and stuff like that, because that the point sets are identical to all of the points in the equivalent set, right? But then you also need to do the right thing for the case where it's not. So this effectively creates this duality where you've got two different, I should say dichotomy really, where you've got two different paths, for the parts where you're analyzing a subset of points, and then ones where you're analyzing all the points in the equivalent set. Yep. and it is important performance optimization. Like we often will find ourselves going down the path where expert covers is true, and we get to skip a lot of the intersection testing and stuff like that.
So you could just have one equivalent set for every region, right? There's no need. There's no.
If you had no regions, if you had no regions that aliased, then yes, right. But as soon as you make a partition, I mean, I guess yeah. As long as you have only if you have partitions, if you had a region tree in which like there was only ever one partition, of any region, right? So like you have multiple partitions nested, right? But like each region has exactly one partition made off of it, right? Then you could get away with just having equivalent sets at the leaves, and you wouldn't have to, expert covers would always be true, right? But as soon as you have any region with two partitions, that create subregions that interfere with each other in non-trivial ways, then you probably end up with equivalent sets, that you need to analyze with expert covers equals false, right? Let's see, do I have a picture of that somewhere up here? I think I do. Yeah, right. Like this picture here, right? Like effectively, like if you didn't have R4 and R5, right, and you could divide the line here, I mean, maybe then you just have two equivalent sets, one for R2 and one for R3, right? And things would just kind of work, right? And then regardless of whether you're analyzing R1 or R2 or R3, every expert covers would always be true, right? But once you introduce subregions that will maybe partition R1 in a different way, then you get partially overlapping stuff, right? Yep. Yep. Any more questions? Okay, Sean should be back next week to talk about the Realm DMA system. And feel free to ping me with questions offline if anybody's got them. Okay, thank you, everybody.